Hello! God, I'm hearing myself double. Much better. Hey. Stream seems to be working. What are you doing? You're not hearing me. Dick. Ah, because you're stupid. You're talking now? Yes. Okay. Well, as the title suggests, I am an engineer that's currently studying to get more understanding of technology. And I thought I would stream my semester project in PLC programming. For anyone not familiar with it, Google Siemens S7 1500. This is the machine I'll be programming with some additional components. I can switch scenes real quick. The top right, you see my setup. The red thing is it's like a little high bay area model that can move on 3 axes. The goal is to make it move the blocks. I'm not sure how well they are visible on the camera, but to move blocks in and out of the storage shelf. Let's see if we can get there. Certainly not today, but sometime in the future. The thing on the right with the motor is just to visualize one of the axes, one of the requirements for passing the passing the grade is, God, what's my microphone doing? Myself. Fixed itself again. Okay. One of the requirements is that when one of the axes, for example the x-axis on the high bay area model moves, the motor turns, not like in a particular way, just in one direction. If the axis moves backwards, he turns into the other direction. So to visualize it moving basically, but it's not like I have to control the speed or anything like that. To the right of the camera, that's not in view right now, it's on my desk, is a little HMI, like a little touch panel. I'll be programming a little visual interface for a potential user to use. We'll see how that goes. That's actually the part I have the least experience with, because in my apprenticeship I already learned most of the things in the program you see here in the middle. We're going back to the top now. That's much better. The program here you see is TIA Portal. That's where you basically program all the logic and plan your whole machine when you have a Siemens controller, which I have. And somebody joined. Hello. It's the Groby. I think I know that guy. Not sure about it though. Well, you just missed my whole explanation. Oh, the power nap is... I'm nervous, man. It's weird. Feels like talking to myself. Hi, Hannah. Hello. Well, since new people joined then, I'll repeat my little explanation of what I'm gonna do. Nothing new. Okay. Well, funnily enough, it was Groby's idea to do this stream. The goal is to work on my semester project. If I switch my view shortly, on the top right you see my setup. I have a Siemens industrial controller. If you Google S7-1500, you'll and go to pictures, you'll see one. They are very commonly used in the industry, and I'm currently studying to improve my knowledge about those guys. So the semester project consists of the red thing you see in the middle. That's like a little high bay area model. It's just a little crane that can move blocks around, and the goal is to make the blocks, make it be able to move the blocks automatically in and out of the storage slots. On the right of it, you see an electric motor with Siemens with a Siemens motor controller. The motor is just for visualizing one of the axes of the crane. So, for example, if the x-axis moves upwards, the motor turns to the right, and if it moves in picture downwards, backwards, the motor moves backwards too. So that's the goal. Also part of the challenge is to make a little visualization for the user. You can't sadly see it in the camera because that thing sits here on my desk. It's just you can imagine it like a touch screen, like a phone or something like that. So, but for now, the most important thing, I'll go back up, is the program you see here in the middle. That's the so-called TIA Portal. It's where you program and plan out everything if you have a Siemens controller. I already have a project because I didn't want to torture everybody with having to set up the hardware configuration because that took me 13 hours. Yeah. So we can focus on programming the actual logic into the into the machine. So, first, just for the overview, load. Okay, let's make it a bit bigger. So, here is my controller, my Siemens controller. Through this connection here, my programming PC is connected. And this here, and I'll jump just right over here, is the HMI, the touchscreen. The guy here left of it is the motor controller, and this thing up here connected through the purple line, through the pink line, is the crane. I'm doing good, thank you. I'm not angry or anything. Oh wait, this is the angry face. You could say I'm pretty tranquil right now. How is the Groby doing? So, this is like our overview, what is connected and how it is connected. Sorry about that. Now, if we here on the left, we have a list of the machines too, like the PLC on top, the HMI, the motor controller. The crane model doesn't need to be programmed; it's already pre set up by the school. Oh, you EP. Well, as soon as we get into the programming stuff, there will be some neuron activation, I hope. Well, main thing, the PLC. I'll refer to the Siemens controller as the PLC from here on out. Ooh, you full of foods. Me too, I had some toast. What did you have? Here in the PLC we have multiple things we can do, like the programming blocks. Like here we have I don't know, can I make this bigger? No, I can't, sadly. Wah. We have our main programming block. You can picture the PLC basically if I open. Do I have paint on this guy? No, I do not. I don't install it. For reference, this is the thing you guys are seeing is my programming server. So it has a lightweighter version of Windows that doesn't have like paint and stuff on it. Oh, you had Indian food. That's very cool. Was it? Did you take the spicy one? Anyway, first things first, the PLC itself needs to know what are the interfaces on the different machines that are connected, like what are my inputs, what are my outputs, how can I talk to these guys. Sorry, my throat is a bit sore today. For this we have the PLC variables, like if I open the one from the crane that is already pre-populated, you can see we have, can I make this guy bigger? God damn it, the Optia portal. Why can I not make this stuff bigger? How dare you? Aww. No torture today. Well, if you won't torture your ass, maybe you will torture your brain. We'll see. I love these emotes. Okay, if I shortly switch to the cam version, in the bottom of the camera you see a little control panel on the crane model itself. Those buttons need to be represented in this list here so that the PLC knows what the crane expects. Like, for example, there is a button that is that drives the x-axis, which is forward and backwards, and that is on the PLC, that is input 128.0, and that is hard-coded in the crane model, and so you have to represent that in the PLC, and you do that through this list. Every input, every output has a specific address that is hard-coded in the model and needs to be represented in the in this variable table. The syntax is actually pretty simple. I said 128.0 that if the basics of computers is like you have 1 bit, and that is a 1 and a 0, like a switch, like on and off, and then you take 8 of those switches, and that gives you a so-called byte. 1 byte is 8 bits, 8 switches. So for our position X button, that's input 128, so byte 128, it's the name of the byte, and we address bit 0 inside this byte. So the very first switch in that byte is this button. I hope that is somewhat understandable. And that goes through with all the inputs. The outputs function exactly the same. They just have, instead of an I as a prefix, they have a Q. I don't know why Q. You can also switch it to an O, but I learned it with Q, so I stick with that. Yeah. This is the one model. Then we have the motor controller. And as you can see, this guy is empty. Because I have not populated it yet. Let's see what this guy can and cannot do. For this, I should have prepared a list that I should have opened before the stream, but maybe I have not done that. Maybe. Maybe, baby. Where are you? You should be somewhere around here. Yes, I need to make kids with it. That's what learning about technology is all about. You make kids with the technology. Let's go. Where is he? The table of his interface is part of the school documentation, and that thing is a damn jungle. Wasn't it somewhere? Instructions unclear. Thing stuck in USB port. This is not it. Damn, they hit that thing pretty well. Well, I can't find it right now. Anyway, it isn't that much of a problem. I'll just do it on another time. Because I can also just start with the crane model. Some basic stuff with that guy. Now, for that, we need another program. It's called OFT2. It's not specific to the crane model, but it's more used to plan out stuff. Like everyone that's familiar with PLC programming has probably heard of GraphCet, GRAFCET. You can picture it basically as an instruction table. Like you start at the top, then you get an instruction, you do that instruction, then you get to another state. And that state is escaped by another instruction. And then you get to another state, and so on. So what we want to do is we want to move the model. I'll start by moving it by hand. So I pull in a start condition. This one. Make it presentable. And this will be our next. This is our second state. This will be our transition. And we connect those. This. And in our transition, we'll say, let's say if button x plus equals 1. Oh, that was the wrong field. I'm going to put it on here, like this. If button x1 x plus equals 1, we need to put here a text field, like that. We need to set motor x plus, that the output motor x plus needs to equal 1, like that. And after this, if it goes to 0 again, he will exit this state. Oh, he needs to go. No, just need to go there. We will exit this state if button x plus equals 0. So if you let go of the button, And we will loop that back around to our start. And we will give that guy a text field 2 to have our start condition defined. Start condition will be x plus is 0. So, no. So, now we start here with our motor x plus is 0, so nothing moves. Then we press our button x plus, so x plus is 1. We move to state number 2 and set our motor to 1, so to move. Then, if you let go of the button, the input button x plus will be 0, and so we exit state 2 and go back to our start state where motor x plus doesn't move. And in the TIAP portal itself, this will look something like this. We need an output. Where is it? Here. Common output. And now we need the motor output. Where are you? Where are you, motor? This is the negative. Here it is. Okay, and now we need our input. Oh, my coral is in the way. I think I'll need to cut that thing out a little bit. Need to cut that thing down a bit for next time. I'm just pulling from the list that we had open before. There's like a little helper window here. Input button X here. So that's already everything. And with this program, we can drive the motor in the positive direction, so forward. Now, obviously, this is just on my computer right now, so I need to load it. Everything in this program is combined with waiting. That's normal. It's industrial software after all. Yes, I would like to overwrite main. Please do. So, now that should do it. Now I need to... Where's the switch? Okay. The PLC has a physical switch where you can start and stop him. So he doesn't just start executing random stuff. Now I've connected online to the PLC so I can see what he thinks. Right now he is in stop. When he is in stop, he doesn't do anything. He does not execute the program, he just waits. I'll go down again so you can see the camera. And now if I press run, he runs my program. And if I make my little box here a bit bigger, bigger. Is it bigger? Yeah, not by much. That's pretty good. Now you see it is blue. Blue means there is a executions. What's with executions? we'll get back to that. With the blue outline, you can see that the state is off. If it gets a green outline, you'll see that it is on. And I'll be moving right over. You'll see my hand in a second. And as seen, it moves, but only forward, because that's the only thing we told him to do. Now we also need to tell him to go backwards, because the rail isn't infinitely long. This we go back over here, and there is something in the there is an action in GraphSet that looks like this. That's a parallel action. Basically, if you have a normal branch in a GraphSet, the program can take either the left or the right branch, or just one of them. And in a parallel instruction, it can take both at the same time. Yep. And we'll delete this connection and just move all of this down a bit. That. Now we insert this over. Roby, I'm still not sure what you meant with executions. Okay, oh, something. So. And now we can make a copy of everything, please. Like this. Then move this over here. Like that. Make you a bit wider. Yes. My TD privileges have left. Sounds like a Groby quote. Fall on. I'm afraid to ask what he's doing. I'm actually afraid. I'm actually very afraid. No, we need to, oh, no. If we branch with a parallel instruction, we need to synchronize with a parallel instruction. That's the rules. And that should do it. Now we just need to, oh, this will be our y-axis, and this will also be, no wait, stop. I am stupid. I am stupid. this needs to be the negative x, and we are not allowed to use a parallel instruction. Because what I have done now is a very simple error that can destroy your motor. Basically, as I said, the parallel instruction lets the program use this branch and this branch at the same time. But this branch is for driving forward, this one is for driving backwards. So if both of them are on, the motor will get in a predicament. Whoops. So, be gone parallels. Groby wants you to tell him something new he doesn't know. Well, I can't do anything against that. He did that professionally at some point. And I have to start at the beginning, otherwise there will be chaos. Thing is, I like to do the manual controls first, and after that go to the automatic controls. Oops. Because I think it builds on each other more nicely, as if you would just straight up go to the automatic. I think that's what he meant, like random fact, only you would know that he doesn't. Random fact. The steam engine, the Flying Scotsman in England, runs at a maximum boiler pressure of about 140 pounds per square inch. Is that obscure enough? Let's continue while we wait for Groby's judgment. But now we also need to add one base state up top here, because our yes, the Groby is satisfied. I am I'm happy to have pleased the Groby. Well, now we also need to initiate this to to 0, yes. And would like a full-time subscription for Turtles Train Facts. Well, Turtles Train Facts is an irregular occurrence, you see. It doesn't follow a set timetable. It exists sometimes. But for the Groby, we'll make it happen. For the one and only. Lies and slander. That you are the one and only. Cancel, stop, cancel. I don't know if it has a cancel option. I'm not sure. Maybe that train has already left the station. You should make it a point redeem, run train fact from Turtle. You know what? Where is my text file? My ideas text file. Here it is. Idea. Redeems random train fact. I'll set that up. Maybe next time on stream it'll be one. I am busy holding Tiddy so I can't chat, and this is what Hannabels does to me. Seems like you're a bad Tiddy holder then. This feels like a trap. This feels like a massive trap. But let's go for it. What is Kenya? I have not heard of that in a while. While you type out the joke, I'll continue with my little program. Now, to drive the motor backwards, we can basically just copy our output we already have, and I just know by heart the name of the negative one. This. Can you fit these nuts in your mouth? Well, no, because you're hogging the Groby. Well, but now we have a problem. Here in our graph set, you can't have the x plus and the x minus active at the same time because the program can only choose one branch. But this is not represented here. Here, if this one is positive, this one will be positive, and if this one's positive, this one can be positive. So we need to lock that out so that that can't happen. You can do that pretty easily with an AND gate. Let's make the same, put negative on the bottom and positive on the top, and then copy this here, like this. Now an AND gate now an AND gate works. You can have as many inputs as you want, basically, but let's go with the two we have. If both of those inputs are 1 or true, it will set the output to true. And I just realized I need to negate this one, like this. Okay, so what happens now? If this button is not pressed, you have a 0 here, so at false. This little dot here will negate that. I'll make it a bit bigger so you guys can see it better. This dot negates that. So the input here will be that this is a 1. Show that if I go online. Show that live, come on. Oh, I need to load program first. Always load the program. And then go live. Yes, yes, yes. Now this input is a 1. And this one is a 0. So if I now press this button, this whole AND gate will be true. Yes. Now you can see it. Now the little dot here is green. If I deselect it. Now here he is green. If I now press the negative button, this dot will get false, negative. So even if I press the positive button, the AND gate won't work. It will never give out a positive signal on the output. Because if I press both buttons, this one will get negative and this one will be positive. If I only press the positive button, this will be positive and this will be positive. I can demonstrate that, obviously. Let's switch to the camera again. This. I hope that makes clear what that does. So now we go offline again, because we don't need to be on the looking into the controller while we program. And with this, we have a manual control for the x-axis. Now, the crane has 3 axes, x, y, and z, or x, y, and z. Depends on the English. So we would need to do that 3 times. These 2 networks need to be copied 2 more times. But anyone who has programmed will know this. You want to be lazy, so you don't want to do that. Let's go up on my pedestal. So what we can do is we can make a new block. We can make a function. We want to program it in FOOP, and we will call that manual control. Without the underscore, and there needs to be FC. Just for explanation, the pink guy up here is a system block that there are certain specific ones I'll get into in the future that do certain tasks from the and get called by the operating system. The function blocks I will probably use in the future. They are like blocks with a memory, so they can remember past inputs, and the functions, they are just called and forget everything after that. So they're fresh every time you call them. And the data blocks, they are meant to store data. I'll show that later when I have to set up the touch panel interface, because that works over a data block. And create. And now we have our new role here. First thing we need to do, we need to make our in and outputs. I don't think I can zoom that in. I need to make that window bigger. Things for next time. And we want to have an input. Let's call it what do we call it? Input button. Let's call it button plus for the positive direction, and input button minus for the negative direction. Like positive would be forwards and minus would be backwards. Our output obviously will be output motor positive and output motor negative. And we will give that a commentary, a comment. So that's just good practice. If anybody except me looks at the program, he does need to understand what I'm doing. And comments are very helpful with that. Motor backwards. No, that's wrong. Put this here, and this is forwards. Motor forwards. It seems a bit arbitrary to do it in such a simple on such simple variables, but if you do it on everything, you get like used to it and do it on the complex stuff as well. Button move forward. We have button move backward. Okay. Now we copy our two networks here and paste them here. Oh, thank you. I'm trying. It's still kind of weird. It feels like I'm talking to myself, which is awkward. And status update. The Groby is tidiless again. On the side note, yes, you're doing good. Thank you. Some tidiless behavior. Well, if you mean me, that is true. I'm open. No, that's bad. No, we won't go there. Okay. Now. Oh God. No, wait, I need to change my face now. I'm more like this. Okay. Okay. Oh, it seems like somebody else has joined. Hello. For context, I'm working on my semester project, which is automating this red guy in the top right corner so he can take blocks in and out of the storage spaces himself, which is the short version of it. Okay, let's continue. Now we have our function that we would like to reuse. But these are hardware inputs. They are hard-coded. They're always the same. And the ones we put in up here are variable. We can assign them. So we need to replace our ix button positive x with our variable. And obviously the same with our outputs. And the big difference we see now is if I go one step back, this one has like these this English turquoise, blue-greenish text on top of it that's denoting the hardware it's connected to, and our new ones don't have that because they are variable. They can be anything we assign them. Okay. Now we have made our function. And if we go back to our main program, we delete these two because we don't need them anymore. And we pull in our function. And you see, we have an input button plus, input button minus, motor plus, and motor minus. Now, if I am here again, Let's put on and to these we can assign the hardware inputs, and to these the hardware outputs. The input button negative and input button positive, and the motors. Well, the motor, it's just one. Negative, oh, that should go here. And the positive one. Very nice. And now we have condensed these two into just this block. And we can reuse this block as often as we want. So I can just copy him down here. And now I just need to replace the inputs with like the y-axis. Say, like this. There's obviously some setting up required as well, because I can literally just change like the x to a y because the names in the table are consistent with each other. That's also something to keep in mind, to have a naming scheme that actually is consistent, which makes, as you can see, this stuff really easy. Now I'm just changing it to the z, and now we have all 3 axes. And as I said, you need to name everything. So this is manual control x axis, this. Then I copy manual control y axis, manual control z axis. Okay. And so we have all 3 of our axes. Let's try that. Load our PLC. Let's go. It has loaded. Let's go online. I don't need this guy here. Okay. Everything's green. If something isn't green over here, we know that we have a problem. But as I said, it took me 13 hours to do the hardware configuration, so I'm very sure that everything is okay. Now, we see our blocks are all green. That just means they are enabled. You can enable and disable blocks, that's these EN pins here. If nothing is connected to them, they're just enabled by default. I don't really know use cases for that. I wrote a program once that had to use them, and it was, for a lack of a better term, that was cancer. Okay, now it is loaded. I'll switch back to the cam view. And you'll see my hand in a second. And as it was seen, it works. Now, let's go offline again. Let's do the next step. There, I'm starting to get into this. Hand reveal. Woo. I should probably turn on the light. Much better. Okay. Turtle hand puppet. I'll put that on the list. I'll put that on the list just because it's funny. And Puppet. Okay, it's on the list. We'll see about it. Now, I'll make it a little bit smaller because then I can see more, obviously. So, the functions are not only useful in... Yes, it would be funny. Yes, it would be. The functions aren't only useful for combining networks together into one block. They are also useful for structuring the program. I'll switch back on my pedestal. Yay! They're also useful to structure a program. So how would we do that? We see we have everything in our main. This block here is called the main program sweep. It's the main program that is called every CPU's, basically every program cycle. And here in this block, we don't really want the actual code. I think there is spam going on. Gone. Okay. Okay. Now we don't want to overcrowd the main program because we want to structure it into different sections. So we will make another function. Our hand mode doesn't need to have a memory because it's only active when we press the button. It doesn't need to remember the last time something happened. So we just can make another function. Let's make fc function. Function. Now my brain is loading. The turtle has entered. Function, let's call it hand mode. Or no, we call it manual mode. That's way better. Manual mode. Oh, we can take our three functions we have in our main program and put them in here. And we delete them out of the main program because they are now contained in our manual. And we want, again, we need our input button plus, but this time we need to specify the axis. Hand job mode. No, I'm not building a masturbation machine. Thank you very much. He's a bit too slow for that. Thing we need to do now is we need to pull our variables from way outside of the main program into our function block. So we have to recreate all the variables we need for our little functions we already have in here. And these are all the buttons for the different axes. X button C minus. So we will also include one more because now we have a hand mode. So we take an input, manual, Let's just call the variable itself manual mode. Oh, manual mode. Let's go with manual mode. I'm not sure. Now let's stay consistent. Manual control. Because the block is called manual control, so we call the input as well. So, and in the comment, we just write manual control on equals 1. That means if the manual, I'm gonna stop here from slowness. Who knows? So the manual, if the variable manual control is 1, manual control should be on. You know what, I'll write that a bit different. Manual control 1 equals on. I think that's a bit better, like this. And I'll open one of these real quick and I'll just copy. It doesn't like copying multiple lines. Let's just copy one and the other. And then copy them through. Oh. So now let's edit them a little bit. Button move backward on the Z axis, forward on the Z axis, forward on the Y axis. Roby, if you want the Masturbator 3000 so badly, maybe you should build it yourself. You're well versed in this type of programming as well. Okay. Okay. Now we have all our inputs, and we also need our outputs, which are all the motors. So we have motor X plus and motor X minus, and I will be lazy and copy that. Y plus, and this will be Y minus, and one more time for the Z axis. Motor, wait, how did I write it here? Motor forwards. And motor backwards. And this is for the Z axis. Oh. I'm pressing multiple buttons at once. And adjust all the axes. This is the Y axis. This is also the Y axis. And this is also, no, this is the X axis. Okay. Now we will assign our variables to our respective functions. Y, oh baby, Y. And outputs as well, so we aren't constrained by it being only this specific hardware output. We want to make our stuff modular. That's the goal here. Perfect. And control. So that's the name for the function. So now we need, now we need to implement our new input manual control, because that is not handled in here, it's completely ignored. The main thing is we just want any of these to work if manual control is true. So what we can do is, as before, we just do an AND gate and put manual control in here. I'll make it a bit bigger to show it like this. Now, if the X plus button is pressed and manual control is off, nothing will be sent to the input of the function. Oh, I made a mistake. I just noticed. Never mind me. It's called manual mode, not manual control. Manual control is this guy. I'm already getting confused. Maybe I'll need to change the names at some point. Anyway, where was I? Ah, yes. If you press the plus button and manual mode is deactivated, so is 0, then nothing will get through to the manual control function block. Same with the negative input. I will not constrain the outputs because that's not necessary, because when there is no input, there will be no output. Obviously, I hope. Let's do the same thing here. Let's put an AND gate and copy manual mode in here. An AND and another AND. A lot of ANDs crawling all over the screen. Now we can close our manual mode block and insert him into our main program. And we see he has a lot more in and outputs than our manual control here below for comparison. Because on the manual control we just had to worry about the plus and the forward and the backwards, and now we have to worry about the forwards and backwards for every axis. There are certainly other ways to do it, but this is the way I thought of first, so I'm going to do it like that. I know best reason. Now let's connect this stuff. Negative x, negative y, and negative z. Then positive x, positive y, and positive z. And let's connect the outputs to the, I will come back to the manual mode after that. Oh, that's the negative one, whoops. And, oh, here he is. And negative here, negative z, z. Y plus and z plus, wonderful. And now our manual mode, I have some switches on the front of the crane model. Which one is it? Where are you? Where are you? Button, button, button. These are all buttons. Ah, here he is. Let's take the leftmost one, like this. Wonderful. Yeah, he is labeled as a button for some reason. The table was pre-made by the school, so I don't know why they labeled it as a button, because it's a physical switch. save that. TIA Portal doesn't save by itself, so if you don't save and you work 5 hours, you'll just lose everything if the program shits the bed. Load. Now it is in the PLC. Let's look at it. Nice. And now there will be another hands-on experience. Switch to the camera. Function is still the same, but in the program the structure is much neater. Wonderful. Wonderful, wonderful. Okay. Now that we have our manual mode, we want to start work on our automatic mode. So what would the automatic mode need to do first? Let's check. He has a start, obviously. We will start with state 1. And after that, we'll go to, how unexpected, state 2. Between that, we will have a transitional condition. Again, for anyone not familiar with with these symbols, this is a standard called GRAFEC, GRAFEC. It's, I think, a French standard, because obviously it is. Because the French are very good at inventing very complicated stuff. I hope I haven't offended anyone. Now, what will be our first state? Let's see. We will have a function here. And this function will be, let's make it a bit abstract. We don't want to write the code itself yet. We just want to know what it'll do. I'll go back on my pedestal for that. Nice. Now, what we want to do is we want to position. So we need to position ourselves. I'll just do the states first, because then I can, from there on, I can define the transitions much better. It's something that works for me. Everyone draws it a bit differently. Even though GRAFEC is very standardized in the symbols, there are vast differences between like how I draw it versus how the next person draws it. After we have positioned on our let's rock again. On our goal, on the position we want to load, we will obviously load block. Load the block. After that, I'll just make a copy of that guy. We will need to, what is this? Import. We need another transition, and let's not make it too cramped here. Only thing I hate about this program is scrolling. You can't scroll with the mouse wheel. It only zooms. After we have loaded the block, we want to position again. on our unload position, and then obviously we will be... It takes way longer to draw this stuff than to say it. And I'm already out of paper. We want to unload. Unload block. After that, thank you, Groby. Appreciate it. Thank you to Hannah, appreciate it too. It's my first time. Well, technically it's my second time. But that was way years ago. And there I played games. Yep. And after we have unloaded our block, we can go back to our start, and let's just call this one our wait step. And this will basically be what the automatic does. In a broad view, obviously. What I did that last semester, because last semester I already tried to automate the crane model. I'm not saying it went well, because he didn't really work. I still got a good grade for it, luckily. But this will basically be what he does. If anybody has a good... I just see my microphone's a bit oversteering here. If anybody has like a good idea what I could do, like something special that goes beyond just moving blocks around inside the spaces, just write it in the chat. I'm open for suggestions. I heard some detecting the kind of bugs. That's a good idea. Problem is, this thing doesn't have a sensor for that. I could do it through weight, theoretically. If I switch to the camera real quick, let's do some more hand revealing. You probably haven't seen them very well. These are the blocks. And these are aluminium, so they weigh a little bit. If I 3D print some, they should be way lighter, and the motors actually have a function where I can monitor the current that goes through them. So a lighter block should have a lower current than a heavy one. But I don't know how well that works, because there's a transmission between it that gears it down quite a lot. So I'll write it down. I need to test that, and we'll see. Thank you for that first suggestion, much appreciated. See, anybody new? Still the same people, very nice. Okay. Now, what I did last semester was I did not draw one graph set for the whole thing, because then I would have to like unfold the positioning and the loading, the unloading and stuff. I think the last semester's project had like 8 or 9 of those diagrams, which sounds like a lot, but it was basically just these plus some other functions we had to do. I hope I'll get by with less this time, but we'll see. I'm totally believing you that you're not doing that. Totally. Okay. I'll just save this guy. Like this will be our automatic mode. And I will open a second one. Let me zoom this program sometimes. I like it because it's free, but it's a bit jank at times. Just like TIA Portal, but that guy isn't free. That guy is actually very expensive. I think a license sets you back a few $100. I got it from school, so yay. So let's start. Our position. I'm just gonna be lazy here and pull up the one I made last semester because it's kind of a headache to do these. Where's the last semester's folder? You guys can see it. I'm on my second monitor here. Looking through my school stuff that I'm totally not gonna show you. Not because of spoilers, but names and stuff and copyright. Here it is. Positioning here. Small and copy you in. Open this guy. This was the guy I made last semester. This is the positioning. It looks a bit scuffed because I ran out of space down here. That's actually not too bad, as you can see again. I'll turn on the grid. I don't like it like this. So, as you can see. Come on. Okay, now we can see everything. We have our start condition up here. I did it with nested graph sets. Give me a number. Turtle, give me a number from 1 to 100. Groby, I'll give you 8. Wonder what he's gonna do with that. So are you winning, Turtle? I don't know. We'll see. Maybe. Depends if I can finish it on time. Now a number from 1 through 30, 16. I'm scared of what he's gonna do. I'm scared. In the meantime, let's continue. We have our start over here, and we just branch here. I can zoom in a bit more to read. Okay,
We branch here and the program can either go to the right or down. It depends if this one is true or this one is true. If this was just a check for a coordinate that can actually go. We don't need that anymore in this version yet. Okay, so we just go down and evaluate our end coordinate. I'll rename this because the variables obviously are not accurate anymore. It was a different program. End coordinate. How I'll program these, we'll see. Not totally sure about it. Probably a data blocker or something. Then we will move, we'll split that up into our x coordinate and our z coordinate, because it's a bit counterintuitive. Normally x and y are the driving coordinates, like forwards, backwards, up and down, but in this model x and z are forwards, backwards, up and down respectively. Yeah, that's just a given. And after that, I'll just here we have another parallel, so both paths can be worked on at the same time. We just look at the left one because they are both identical. Here we just make a comparison. We know our end position. Obviously everything is in German because I had to do it in German. Translate that real quick. End position and actual position. Okay. So we have our end position that we know and our actual position which we should know. We'll get how we know that later. Now we compare the two. If the end position is bigger, that the number is bigger than the actual position, we know we need to move forward. Otherwise, we need to move backwards. That's why this is just a normal branch that can only choose one side, because we don't want to drive forwards and backwards at the same time. That's unhealthy. Okay. Now, this guy here is describes something that I guess is very easily missed. Just translate that. I can't do two things at once. I'm not that good. Okay. So we want to stop when our end position equals our actual position. But, big but, this will never happen for a very simple reason. The position indicator on the motor has a very fine degree of resolution, so he will always, the motor can't stop that precise, that it is exactly the same value. So what would happen is he would oscillate back and forth around his goal, around his end position, and that would be bad. Firstly, because the motor doesn't like it, and the mechanics also don't like it. Plus, the program would be stuck in step 3 or 4, and this condition would never be true. So what we have to do is we have to put in something like a tolerance, and I just put in like 2000 steps, which is, I think, what was it again? I think a millimeter or two, so not that big. And that just gives it a certain distance where it can stop, and the condition will still be fulfilled, so we can continue. After that, if both axes are in their respective positions, we can go to S5, which just returns us, which would have returned us to the main graph set, because this is a subgraph set. Yeah. Anyway, in any case, we would be finished with our positioning, and we would be on the position we would have wanted to be. You want to save. Now, the programming of this, no, wrong program though. The programming of this relies on that the position is accurate. And how do we make the position? How does the program know where it is? My talking breaks. Help. How do we know where we are? Well, there is on the model itself. I'll switch to my camera real quick. I can't talk really good because my microphone's in front of my keyboard, so I'll just show it and explain what I showed after I have shown it. So I hope you saw that. Where my finger was is a little sensor, and that sensor basically tells me you are in your zero position. And if that is the case, I can just set my internal position counter to 0. And if I can do that, I can start counting again. If I drive forward, I count up, and if I drive backward, I can count down. Now, how would that look? Let's see. I made that last year as well. Last semester. It was not last year. And I have it somewhere here. Copy from my laptop to my PC. Very nice. These two guys. Oh god. OFT is starting to crowd my desktop. Help. And let's. No, these are the backups. They're also backups. What? Where is it? Ah, this is one. Here it is. Okay. Open these. Okay. So how do we know? How do we count where we are? Yes, I just opened 2 graph sets because this one was too wide for one page. Okay. This works as follows. We take our actual position and calculate the difference to the position we were last time we looked at the counter. I have to get into that as well again. It's I think the most complicated thing in this whole program. Yes, that is pretty poggers, if it works. So Okay, we take the motor position. This is the motor position. And we subtract the motor position, the motor position we had last time from that. So we get a difference. And that difference down here is compared to the value either negative 32,000 or positive 32,000. And depending which one is true, we will add an offset. We will add or subtract an offset. Like this 65,000 offset. And this will give us our new actual position. I can show that a little bit more comprehensive. Like there is a really nice graph in the school book. I think I can show that. See, where is it? Everything's in German. Because I am from Switzerland. Where is it? Oh, I think it's at the very bottom. I think it's like page 50 or something. Oh, damn. It's like the first time I searched for it. Oh, God. Chapters are just useless. I really want to show it though. Way. Let's see. Manual. Oh, here it is. Should be page 160 somewhere. Ah, here it is. I was looking for this graph. Oh, let's do some graphs. You can imagine the position, oh God, I don't have the English word for it. I had technical English, but this was not in it. Encoder, that was the word. The encoder. The encoder sits on the motor itself and turns with the motor. And the encoder just gives out the value. The encoder gives me a value that rises. When the motor drives forward, the value rises. If the motor drives backwards, the value falls. That's this graph here. We're just looking at this left side. Now, this value is not endless. Oh wait, I go back on the pedal. pedestal for this. So this value is not endless. So up here is the value about 65,000. Then it overflows. 0. And then it starts counting again. Same goes back when it goes backwards. When it reaches the lowest value, it jumps back up to the highest value. And I need to detect that with my program, because the distance between this point here, wait, can you? Oh, you can't even see my cursor. Sorry. The value between this 0 here and this top point here is, I think, about 20 millimeters. So if I don't take that into account, my actual position will desync very fast. Now, here, this is what the school says you should do. I will do it a little bit differently, because our teacher showed us a way better method to do this than the school literature itself depicts here. But to get an idea, it's pretty good. You have your start condition again, and we just do the difference. We take our actual encoder value and subtract the previous encoder value. So we get the difference. You can ignore this is just housekeeping. And this difference will be compared to negative 32,000. Is it smaller than negative 32,000? If the answer is yes, we know that an overflow has happened, and we can account for that by adding 65,000 as an offset. If it wasn't the case, we look if it is greater, if the difference is greater than 32,000. If it is, we know an underflow has happened, and we can again add an offset of 65,000. Big difference here is, you see, between position and difference, here it gets subtracted and here it gets added. That's the difference between the over and underflow. If nothing has happened, so basically we stayed inside this range here, like on this flat, then we can just directly add the difference to the position. Keep in mind the difference can be a negative number, and if you add a negative number, you subtract it. It turns into a subtraction. And that's it. That's basically what I did last semester. Spoiler, it did not work. It went horribly wrong and everything crashed and burned. Well, not really. There is overload protection. Nothing happened. Roby, you are very colorful. Okay. I need to drink something real quick. Very good. Now, with my throat freshly oiled, because obviously I drink oil, we may continue. Now, we want to change that up. First of all, I'll just replace this with a normal start, because we aren't doing any of these fancy subgraph sets this time around. Now, what I want to do is I would like to decouple this whole subtraction here is dependent on the physical input itself. And I would like to decouple that so that it isn't dependent on the physical input, but it gets written into an internal variable, because I can control the internal variables much better than I can the physical inputs. Plus, if I need to read it in again, it's generally not a good practice to have an output as an input, or an input as an output, basically. That's bad practice in PLC programming. So I would like to have that decoupled. It also makes the math a bit easier with the offsets. I actually prepared that because it took me quite a while to figure it out. I just need to... Obviously, I'm very well prepared, as you see. So I have that ready here, obviously. Groby, how's your number game going? I said 16 last time. Let's see. It should be... Where? Chaos reigns in my files. Ah, here it is. Okay. Is it actually... You need another one from 1 to 100, then 1 to 30. Okay. Let's say 32 and 4. Oh. I just confused my browser window with the OpenStream with OBS. God. Sometimes I'm very lost. Okay. Let's do that, and we will make a new function. Because this guy... no, this guy needs a memory. Oops. Happened? What notification? Oh, just the family chat is alive. Help. Family interactions. Now, since we have to compare a variable we have in this program cycle with a variable we wrote in the last program cycle, we will need to take FB, a function block, because these guys are coupled to a data block, so they have a memory. They can remember stuff. We just call him FB. Let's call him, what do we call him? Let's call him encoder counter. I can rename them at any time, so if anyone has a better idea, I'm open for suggestions. So, I don't know how good you guys see that, but the great difference in the list is in the list on the left is that the function blocks are blue and the functions are green. Here in the interface, they are exactly the same. You program the same, you make the in and outputs the same. So there isn't much of a difference in that regard. Now let's pull up my PDF. Okay. First, we need to do I'll just pull in the actual thing I made, and after that I'll modify it so it works to the actual use case we have here. Because the one I have is a bit generalized. We'll take 2 move blocks. The move block is quite simple actually. It could also be called copy because the value on the input is just copied to the output. You can do quite a lot with them. The coordinates for the oh god. Oh, it's funny when I speak a lot of English I start to forget words. Have fun in the sauna. Thank you. It'll be interesting if it will work. Some more you want some more numbers? Let's say 24 and 6. Oh, now there's towards so. Probably the compartments in the shelf will be stored in a list that I can access through those move commands. But that's in the future. We'll see how that actually goes. Back to the task at hand. We need some inputs. Here's the input table I made. Bye, Groovy. Have fun in the sauna too. Don't overheat. I have an input that is the reset. We will need that for the resetting of the counter value. Then we obviously need an input that is the encoder. We just need to make one encoder, but because this will again be a function block that we will use multiple times, so one for each axis. On the output, we will have an integer. I'll explain in a second what it is. Integer position. Actual position, a bit abbreviated. This will be a double integer. Now, till now we have only worked with variables that can be a 1 or a 0, so true or false. There are other types as well though, for different purposes. The integer we have here is you can imagine it as a whole number from, I think, negative 32,768 to positive 32,768. So I could be a bit off, but it's around 32,000. the thing is you can just count whole numbers with it. So no commas, no decimal places. That's the English. No decimal places here. Or if you want to use decimal places, you need to use something that's called a real, R-E-A-L, real. Reals can represent decimal places for quite a few spaces. They are like there's another data type that's way more well known. I think, is it float? It'll come back. My memory will come back. Anyway, we won't need reals because our position will only be whole numbers. That's precise enough for our purposes. We just need to specify the size. As I said, int is about negative 32,000 to positive 32,000. A double integer then is double the length. I would need to look it up. I think it's positive 65 something thousand. The negative of that, don't quote me on that though, that's just from memory. The int. Let's ask Dr. Google. The int length. Oh no, it's negative 2 billion. No wait. Oh no, English notation. Yeah, negative 2 billion to positive 2 billion. Yeah, that's the double integer. The thing with the doubling is it doesn't double the number, the decimal number itself, but the bits that are usable. An integer is, I think, 16, and a double integer then is 32. That's why you say it doubles. Okay. Then we also need some internal variables. The variables here in and output are obviously in and output. The static ones are only internal in this block. They're only used inside here. They can't be accessed from the outside. We need another digital double integer position. Oh god, I gave that one a really weird name. Position inc total stat. I need to rename that guy because I don't really know what that stands for anymore. First counter value stat. I think stat I used for static. It'll be fine. And the static variables are also the ones that will be carried over through multiple program cycles. Now, below them are the temp variables, temporary. They'll get reset every program cycle. So they start every cycle with 0. And this will be an integer different counter value and double integer different counter value. And the add active. This will be our over or underflow variable, if I remember correctly. It has been a while I looked at this, I have to admit. Now we have our moves, and the only thing we use these guys for is they will initialize our values to 0. And and the values they will initialize are the temporary variables, because we want to make sure that they are actually 0. Now, oh yes, I need to guys to double integers. You want to be double integers, you also want to be an integer, and you want to be a double integer. I think that should be everything, and that works again. TIA-Portal checks to a certain extent that the variables are compatible with each other, and some of them it can even convert between. Like it can convert double integer to an integer automatically, but if the double integer is too big for the integer to fit, you'll just get data loss, and that's bad, obviously. So you want to avoid that. Now, there's one thing here. This guy won't work like that, because the output here is 0. So it will set the variable to 0. But we want the variable to be 1 on startup. That's why we can, that's hard-coded in the controller itself. That's a variable we can use always, true. There's also always false, and the only thing these variables do is what the name says. This one is always true, and always false is always false. Okay, continue in our next network. Oh no, I forgot the name. This is initialization. We initialize our critical values that we want to be certain of. Next thing, we will reset our counter value. But we only want to do that if, let's put the output in first. Oh no, that's another move command. If you want to write numbers in variables, you basically always need move. That's pretty inevitable. We need one of our static variables, input position incremental total stat. Exactly. We want to initialize that to 0, but now we have one of those few cases where you need the enable pin. Because the move command always, in every program cycle, writes its input value to the output, we need to control when to do that. Because obviously we only want to reset the counter value when it is being reset. So if the input reset is true, we enable the move, and the move will copy 0 into our counter value. Nice. And next. I need to actively translate that because I wrote it in German. Because at the time I made that, I wouldn't have thought that I'd be streaming this. Driven increments per program cycle. The controller obviously is a computer, and so it can do math. Here we have additions, subtractions, multiplications and stuff. The thing with industrial controllers always is like how much calculation power you have. They aren't a gaming PC. Most of them are like comparable to a like a 90s computer. They don't have much RAM, they don't have a fast CPU, but that's also not really necessary because you want to write optimized code and not do the heaviest calculations on these things. I think it has a lot of functions. You can calculate the square root and cosine and tangents and everything, but if you can avoid it, you should. Like where I work, the PLC is really just controlling the motors itself and nothing else. It has the sensors attached to it, it has the motor attached to it, and that's it. It doesn't know where everything goes. That's the responsibility of a system that is one step higher, that has way more power than the controller itself. Well, I started rambling. Now let's see. We want to have our actual counter. I'm confused right now by myself. Very nice. I actual counter value. I forget something. I probably forgot something. Ah, no, I just gave that guy a different name. Actual counter value in my PDF is the input encoder. Oh, who would have guessed? And this will be paired to you, and the difference will be taken. Okay. Ah, this must be an integer. That's one of the things with the data conversion. Always have to be mindful of that. I just tried to write an integer into a double integer, which in itself isn't that big of a deal, but it doesn't look good, basically. So what we do now, we take our encoder input, subtract the the value we had last program cycle, and this will give us the difference. First step, that part. You know, and now, even though the PLC can convert between data types by itself, there is an extra block that is only meant to do that. And we're gonna use that because that's the nice way of doing it. And different counter value. Okay, and now we explicitly convert from an integer to a double integer inside of this block. There can still be data loss if you like do it the other way around, from the double integer to the normal integer. But this is the nice way of doing it, because another person that will read your program will know that you do it. Because if I just, this is a double integer value, and if I just put that guy here, you see there is a little block here. That's an implied data conversion. And the problem with that is that's very easily overlooked, and if somebody that isn't you reads that code, he doesn't know that that is there. So it's mostly just to tell a not knowledgeable person, somebody that isn't knowledgeable with your program, that you are doing a conversion. Again, programming practices. Now we are getting to the meat of the whole thing. If you guys remember those comparisons with the 32,000 value, now we get to that. Driven increments, and we are not, this time we are not comparing them to 32,000, we are only comparing them to 10,000, because the encoder is connected to the PLC, obviously, and the PLC has a cycle time, has a program cycle time of a few milliseconds, and the encoder updates way faster than the CPU runs the program. But in the time the CPU runs one program, the encoder can't move, is not physically able to move more than the 10,000, basically. So we don't have to compare it to the whole range of 32,000. We can also just compare it to 10,000. But if you compare it to 32 or 10,000, doesn't really matter, because in the end, you only want to detect the sharp spike in the value changing when it under or overflows. So if you check for 32,000 or 10,000, doesn't really matter. You just need to check for a value that is, I think, greater. Yes, you just need to check for a value that is greater than what the encoder can cover in one program cycle of the controller. I hope that makes sense. I'm not sure myself anymore. But let's continue. I'm glad I prepared that stuff. Now, I'm not building that in the order that it will be executed in. That's just something I do for some reason. I started that way back when I learned this stuff. It just grew on me like that. Don't know why. Okay. Doesn't wanna. I'll populate this stuff real quick, and then I can explain it. Yeah, I know I need to put a data type in here. Different counter value, and then I need the again, and I want to inherit that negative 10,000. So, okay, I've populated that real quick. From left, the program is always calculated left to right, top to bottom, so we'll start here. we have the different counter value, which is just the difference between the current counter and the counter last program cycle. If it is smaller than negative 10,000, this will be true. So we continue to the right. If not, we just continue to the next program section. Now let's say it is true, we continue here. This variable add active will be set to true. So we know we had either an over or an underflow. And no, so we know we had an overflow. Or God damn it. No clue about my own code again. Anyway, we will set this this variable, so we know that we had a special condition that happened, and I wrote in this number wrong. Very nice. 65,535. And then we make an addition. We take the double integer from our difference and add 65,000 to it. And this rewrite into the same variable again. This works because, as I said, the program will be looked at from left to right. If it comes from here, it will see the old value, adds 65,000 to it, and then writes it again into the same variable. That's it. And now we have the new value in our variable. And if it comes back in the next cycle, it will read the now old value again, add 65,000, and write it again in the same variable. Since this is not the only condition, we obviously need more. It is greater than 10,000. This will be mostly the same, but here, this guy is a condition. Oh yeah, I think it's coming back to me why I did it like that. It needs to be like this. He needs to be not active. Okay, so since the program is looked at top to bottom, we need to make sure that we don't add 65,000 and then subtract 65,000 again, because that would just lead to nothing. So we set a variable here that prevents the subtraction from ever going through. So if the overflow is true, it sets the add variable, adds the value, and then the add variable, because it is true, will block the subtraction operation from happening. If this one wasn't true and it can go straight down here, the add variable will be 0. Here it is inverted, so it will be 1 on the AND gate, and the subtraction operation will go through. Complex shit. You obviously need to compare it to positive 10,000 this time, but otherwise everything is the same. Yeah. And now in the end, maybe you guys noticed we have only worked in our temporary and static variables. We have not yet written anything into our output. Our output still contains the value from the last program cycle. So we need to update that. Save actual counter in last. I'll refine these when I have time later. I won't do that on stream. Oh no, we are not yet writing to the output. First we need to make another move command, because of course we do. For that we will take the actual encoder value and put it into the last encoder value. And now I can actually rename that to something sensible. Last encoder value. That makes way more sense. Could have called it that from the start. Because now we have used our encoder value and need to save it for the next program iteration. Because remember, we take our encoder value to calculate the difference that we use to determine if we have an over or underflow. Now next will be the calculation of the total counter. Actual counter calculation. And this is basically the, in the graph I showed, it's the third option. When there is no overflow, no underflow, then it just adds the actual counter to it. Where do I have my math functions again? Here, add this. We want inc total. Di and the di different counter value. Yeah, okay. It can auto-detect what data types you put in the add function, but I like to set it manually so it can't randomly. So I can't have the problem of it randomly flipping to something else when I open the program and the TIA portal. And, okay, so now I actually know again what this is. I'm discovering my own program. Oh my god. Yes, that is just that it's static variable, but this is my internal position. Position internal. The position total. Yeah, let's call it that. Position total. And again, we have our difference that we calculated at the beginning, and since we have no over and no underflow, we just add that directly into the position total. And now what I said comes. Oh, this is the last one. Actual, oh no, actual counter total right in output. Now we are here. Now, since we have done everything in our internal variables, we have to write it to the output variable. Like this. Oh, that's the wrong one. This one. And so we programmed the encoders. Man, it's quite a lot complicated, quite a lot more complicated than I remembered. But that should work now, and if we pull this guy in here, we get prompted to make a DB, a data block. I just renamed that guy a little bit. I have a different naming scheme here. This is the data block encoder counter for the x-axis. We need this guy 3 times, but we have to give every one of them their own data block. Because if we don't do that, then all of them will read the same values. And if they all read the same last values, then that would not work, because the last value of the x-axis will not be the same as the one on the y-axis or the z-axis. Y-axis. And db counter z-axis. Okay. Obviously, that stuff doesn't really do anything right now, but we can test if that works. Yeah, I forgot to load again. Let's load you. Oh, forgot something else too. This won't work. I have not connected the physical inputs. I'm not really certain anymore which ones it was. Ooh, I think this one. The physical... Why are you not? The physical encoders are represented in the variable table as well. They send you the data as a word, which is another data type that is 16 bits long. A word, if I remember correctly, a word just represents a number. As it can also represent a number like an integer, but only positive values. Why are you red? Oh, I put them on reset. That doesn't work, obviously. Oh, Y and Z. And for reset, I would like to have the end switch. Is it this one? Could be this one. End switch on negative X, end switch on negative Y, and end switch negative Z. The model itself has an end switch on the negative end and on the positive end, so on forward and backwards. And I think the negative one is the one on the backwards. Not 100% certain though. Let's see. Let's load. Loaded successfully. Let's observe. They are now obviously all over the place, as you can see. because the encoders themselves don't start with a value of 0. You can zero them out through a command you set in them, but that's why I want to decouple that from that's why I want to decouple this value from the physical input, because resetting the encoder itself is again not really nice to do. It works, also works reliably, but it's not funny to program it. I'll switch to my camera again, turtle on the floor, and let's see if the axes will count and reset according to what we want them to. Let's see. The x-axis seems to work. It has reset to 0. And now let's see if it counts up. And it does. Very nice. Now this is also something that is very convenient with reusing functions and function blocks. I have just tested the x-axis. And I don't need to test the y and z-axis because if I know the x-axis works. So I know the other two do too, because they use the exact same code. Very convenient. And if I'll have to do some more analysis if it really counts correctly. And if the over and underflow do actually what they do, but I have been streaming for like 2.5 hours now, and this stuff isn't really that easy on the mind. So I'll probably call it a day. I don't know when I'll be streaming again, but since I don't have I have autumn holidays right now, it will probably be through the next week always. If it happens, it will be in the evening in, I think we are UTC +1. Like just look at the Zurich time zone. Yeah. In any case, I thank you for watching, and hopefully we'll see you through the next week. Bye.